Is that one?
Nope. There we go. Okay. Right. Okay. Let's see. I'm a little behind today. I'm sorry. Okay. Sarah B. Yep. Claire. Matt. Luke. Yep. Jaden. Emma. Liza. Yep. Stuart. Ethan. Manya. Olivia. Kashal. Diego. Darwin. Sean. Jules. Joa. Matthew. Perfect. Colin. Emily. No, Emily. Rennick. Sarah T. McKenna. Okay, sorry for the late start here. Let's see, yeah, 30 seconds late. Okay, so last time we just kind of barely scratched the surface of this new section called change of variables, and it's a variation of the substitution rule. So the substitution rule is a single variable calculus thing. Written by this equation, we tend to know it as, well, it's that thing where if, you have some, function of one variable that you just decide to let equal to another variable, and then you kind of plug it in and you do the thing, right? And then one integral turns into a different integral. Okay. So I want to view that as a less of an algebraic thing. Yeah.
Do you mean is that U substitution or would that be
Yeah, I call it the substitution rule because there's really nothing about the letter U that's important here. Here I'm using T, for example, but yeah, it's the same,
okay.
Same thing, yeah, right. So I want to take a totally different point of view on it. I don't want to think of that as being an algebraic tool for manipulating symbols around, right? I want to think of it as something that's a little bit more sort of geometric, a little bit more sort of, well, there is a domain over here, and the substitution function is a function that pushes you over to, well, another domain over here, right? And so there's an integral that happens on an interval on the x-axis, and that is going to be rewritten as another integral that's taking place over here on the t-axis, as I have things set up here. Okay. All right. So first thing I want to do is talk about this idea of pullback. And I, in a rush, said a couple things about this on Friday, I guess it was. And I want to do that again so we don't rush through it. It's just kind of how functions work from a certain point of view. When a function is like this, points go that way, right? If I have some value, I'll see if I can hit better here. Points go like that. If I have a value of t, plug it into the function, what's the result? Well, it's a value of x. So points go left to right. Expressions do the opposite. The idea is if I have some expression involving x, I should use a different color here. If I have some expression involving x, the act of plugging in, right? The act of taking, well, here's the formula for x. When you plug that in for x, notice the expression goes the other way. That's just how plugging in works, right? It's a little counterintuitive until you look at it and think that, well, but yeah, that's just what happens when you plug in. Okay. All right. So this is this term pullback. is a nice term that we're going to be using a lot to describe the fact that we are, in fact, going backwards through the direction that the function is actually going. Okay, all right. Okay, so a lot of the pullback is pretty straightforward. X pulls back to, well, g of t, because that's what it is, right? And the bounds are not a hard pitch, I think. If x is equal to g of a, well, that means that that t would be equal to a, because again, that's what g does. Just plug in the numbers and see that those work. Likewise for the upper bound. And the one thing that's tough on this picture, though, is the question of, okay, well, yeah, but what's the deal with dx? How do I plug in for dx? And again, I don't want to take an algebraic point of view on this, right? We know how to write the symbols down. But what is dx, and how can I think of that geometrically? And the argument is to say, well, I know what functions do to points. Let's see here. I'm going to see if, yeah, here we go. I know what functions do to points. Point goes to another point. But I also know what functions do to changes, right? The derivative is a relationship between input changes and output changes. And so I want to think of this interval here on the t-axis. I mean, it's an sub-interval. It's a piece of size, sure, right? But I want to think of it as representing a change. And we know what happens to changes. Input changes relate to output changes, right? The relationship between input changes and output changes is the derivative. G prime relates input changes to output changes. And therefore, G prime relates input sizes to output sizes also. All right. And so with that noted, this dx here, that dx, well, it represents the size of this output piece, this subinterval, right? And what is that dx? How does that relate to the input subinterval dt? Well, the relationship is that the derivative represents how much bigger, you might say, the output change is compared to the input change. And it's what I like to call a stretching factor, because it's like that little dt interval in the domain. In what g does to it is, as it's moving over, it gets kind of stretched out, perhaps to bigger. And by the way, it could be smaller, right? Maybe g prime is less than 1, and it's getting squished or whatever. But whatever it is, it's the number that you multiply by input size to get output size. So calling it a stretching factor. How are we doing there? Anybody willing to buy that? Okay. Okay, so what's the upshot? Why is this important? What have we recovered? Well, we have the substitution rule, which we already knew, and right. So what's the benefit? The benefit is that this is now reconceived in a way that's going to allow us to do something importantly similar in 2 dimensions for double integrals instead of single variable integrals. And that point of view, I think, is really important, actually, for being able to generalize to 2 dimensions. So the algebraic point of view is not particularly helpful. But let's think about the analogous situation. The analogous situation would be, I have some region. I'm making it a rectangle for reasons why you'll see in a minute. And let's suppose we look at its image, and again, g being some random function, who knows what that image is going to be. It's going to be some wacky shape. And now let's suppose that I want to do an integral on this wacky shape. Well, let's argue a pullback. If x and y, right, are functions of u and v, right? You got X and Y are functions of U and V. Then, okay, let's just start kind of plugging in. What is X comma Y? Well, it is literally G of U comma V. That's just what the function is. So plugging in, again, pulls the expression on the right back toward the left. And then let's see here. Oh, yeah. What happens? What's the domain? If X and Y range over these values here, how do I get X and Y to range over those values? Well, you get X and Y to range over those values by having U and V range over these values. And again, we come down to, yeah, but what about the differentials? And what's the, this input size here? Let's see here, I'm making a mess. Let me do it like that. This input size, oh, pencil mode. This input size here, that little piece of rectangle, probably not the same size as its image. After all, this function G takes points and moves them around in random ways, and the things could get stretched out and deformed. And so that dA that I've got here on the right is not necessarily the same size. It relates to the green piece of size by way of some factor. Again, I'm going to call it stretching factor. That's right. So what is that stretching factor? How do I relate output size to input size? Well, we need to know what that factor is. So for the moment, I'm just going to tell you the answer. This thing called the stretching factor, there's a formula for it. And here it is, this stretching factor. It turns out, and we will see why pretty soon, but it's the absolute value of the determinant of the derivative matrix, as it turns out. So again, we'll see why later. So punchline, though, it's really just a pullback and stretching factor strategy, just like this point of view that we decided to take on the substitution rule. The substitution rule is really, it's pretty much just, yeah, we're kind of taking things that were written in terms of X, and we're in some sense just kind of plugging in. We're pulling back through the G function to rewrite everything in terms of T, just like with substitutions. So a lot of people think of, and I encourage this, this formula down here. This is the change of variables, what we call the change of variables formula. It's really just a substitution rule in 2 dimensions for double integrals. All right. Okay, why would we want to do such a thing? Well, let's revisit. Why did we like the substitution rule for single variable integrals? And in most cases, the reason we like the substitution rule is because it allows us to change our integrand, right? Y'all have done a bazillion integrals in your lives, and it's golly right up to, it might be the best tool that we have for figuring out how to find an antiderivative, which of course is, I mean, once you found the antiderivative, well, you plug in the A and the B and boom, you're done, right? It's just, so being able to find that antiderivative is all the work. So having a tool that allows you to change and get a different integrand, possibly turning a hard one into an easy one, big deal. Okay. That said, let the record show the domain changes too, right? What had been going from there to there, instead, now going from there to there. So who cares? It's just numbers that you're plugging in at the end. It's basically irrelevant. Not so with substitutions. In fact, arguably the most important reason we'd want to do this trick, the most important reason we'd want to do a pullback, is because the domain over here is terrible, right? Think about our, the way we slice up double integrals. You slice either vertically and then horizontally or vice versa, and try not to hit a corner. if you possibly can, right? Well, my gosh, I think I'm going to hit at least 3 corners on this. That's just, oh my gosh, this is just a nightmare, this shape, right? So having a way to take an integral here done on a super ugly domain and being able to pull back and turn it into an integral, that a perfectly nice, happy integral happening on our everyone's favorite domain for a double integral, a rectangle. That's why this is awesome. Yeah, everybody see the, okay. All right. Okay, so now I owe y'all, it remains an explanation of why this is the stretching factor. And we'll get to that in a few minutes. Oh, real quick before we dive into an example, a little bit about notation. Now, of course, the derivative matrix is this, and that's just that's old news. Y'all have seen this. You know, the way we write down the derivative matrix long ago. But this actually suggests an alternative notation that I think is fantastic. It is a little bit sloppy in a way, but it's just super convenient. And that is to observe that what we've got here, we're looking at the partials of X and Y, aren't we? And so, well, let's just kind of recognize, okay, we're looking at the partials of X and Y, and we're taking their partials now with respect to U and V, right? So this notation here as a shorthand for, yeah, I want to take the determinant of a matrix that represents the partials of these variables with respect to those variables. It's really compact and convenient. And it has some other benefits that are also really nice. I'll talk about in a second, but first, compact and convenient. Now, my complaint about this notation, y'all might even be able to anticipate it. Y'all know that I've complained in the past about writing things as fractions that are not actually fractions. This takes the cake on that, right? I mean, is this a fraction? No, it's a determinant. Determinants aren't fractions. We're writing it as a fraction. It's clearly not a fraction, but I'm going to write it like a fraction. And ultimately, the reason why is because it behaves kind of like a fraction, as it turns out. And so, you know, like I say, a little sloppy in the sense that we're misrepresenting it, but we're misrepresenting it in a way that really models how it actually behaves pretty nicely. So this is a, you know, I'm actually very happy to sweep the formality under the rug for the convenience. Yes.
Why is the derivative matrix called DG when it's not like dx dg, and like we're not, like the G doesn't show up in the partials?
Well, because I hit the wrong button here. I'm sorry. Yeah, G. I mean, it is showing up because G has coordinates X and Y. Right. So this, when I say partials of X and Y, those are the components of G. Is that cool? Yeah. Okay, so let me show you one of the ways in which this behaves like a fraction. Look at where it goes. This thing being the stretching factor, being as it goes right there. What we've got then is, let's see here. When I write this equals that, what I get is, colors. I get absolute value. Oh gosh. Partial XY, partial UV. Come on. Sorry, V. That's what the stretching factor is. Times du dv. In fact, let me put this over here. That is what that is. Whereas over here, the dA that I replaced it with, what does this dA represent? It represents area in the XY plane, which of course this integral here could just as well be written with that as dx dy. So now again, a full apologies for the crime I'm about to commit, but it's as if that du dv and these, you know what I mean, kind of u's and v's, it's as if they cancel, thus leaving you with partial xy representing the dx dy. Now, again, that's not what's happening. This is not a fraction. There is no cancellation. That's not it at all. But it's kind of like it. It looks like it, and it's as a notational convenience is kind of satisfying, right? I mean, at a minimum, it's memory tool kind of convenience, you know? So again, don't overinterpret that, but there are going to be situations where you're going to be unclear whether, wait a minute, should I multiply by this thing or should I divide by this thing? And having it as a fraction is going to help keep us going in the right direction. Okay, all right. Okay, let's do an example. I've got a function here. X and Y are functions of u and v. There's my function. I'm looking at the unit square in the UV plane. And if you take points in that unit square and plug into this g function that's given, by the way, don't worry about where that came from. We'll talk about how to make choices for g's pretty soon here. But if I plug into that given function, then what comes out? Well, I get, as it turns out, a shape that looks kind of like this. And now that shape, suppose that's the domain for an integral I want to compute, right? I want to compute maybe the mass inside of that thing, or I want to compute the number of people living inside of a county that's shaped like that, or, you know, what have you, right? So we got to do an integral on this domain. We observe that if we start slicing up this domain, then bad things happen pretty quickly, right? Slicing this way, for example, well, I slice through a corner, and then you continue slicing, and I again slice through a corner, right, before I finally can, you know, finish. So this is going to be at least 3 separate integrals. If I just kind of, you know, go at it, you know, directly. Okay. All right. Highly undesirable. Okay. So that said, I have that my domain is an image. It's the image of a more desirable shape, as it turns out. It's the image of the unit square. I like the unit square much better. I'm going to say, let's do a pullback. In order to do the pullback, we need to know the stretching factor. I'm going to go ahead and compute our stretching factor first, because we know we're going to need it. The stretching factor here, right? It's various partials. Y'all know how to do partials and the symbol of derivative matrix. Don't forget the stretching factor is the determinant of that derivative matrix. And partials are easy, determinants are easy, and you can punch up that this is our determinant. Okay, everybody good so far? Yes.
How did you know you needed to do a pullback?
Oh, I've just decided I wanted to do a pullback. I don't have to, right? If I want to slice this up and hit these corners, whoops. If I want to just slice up and hit corners and do 3 iterated integrals, there's nothing stopping me from doing so, but I just don't want to. And so what I'm doing is, you know, as we always do when we compute integrals, I'm flailing around trying to find a method that might make my life easier.
So is it not like in Calc 2 when you try to do an integral and then you just have no way of taking the antiderivative, so then you do like a u substitution?
Yeah, right. So
there's nothing else you can do.
Well, that's right. So with in Calc 2, our motivation is usually that the integrand's a problem.
Right.
Here, it's very often the case that our domain's a problem. And I claim that my domain's a problem here. I cannot slice this either dx dy or dy dx without hitting 2 corners. And so, bummer. Is that cool? Yeah. 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 Okay. So we've got our stretching factor. Wait, slow down. Do we? don't forget, the stretching factor is not just the determinant. The stretching factor is the absolute value of the determinant. That is important. So we need to worry about that absolute value. And this is not one of those situations where you can just kind of drop it at some point, right? You've got to have the absolute value. Otherwise, the work is going to be wrong. And it's importantly wrong. So how do I take the absolute value then of this thing that I just got through computing, right? How do I get that absolute value? And sometimes it works out very conveniently. In fact, surprisingly often it does. So for example, I claim that I can just look at this expression and instantly conclude that it's negative as follows. In particular, I claim I know something about you. Here it is. There's you. And check it out. U apparently is always between 0 and 1. It's right there on the picture, right? U is the variable, one of the variables in my pullback domain. I know what my pullback domain is. And by inspection, it's always between 0 and 1. And then analogously, V, I know all about V. There it is. Also, always between 0 and 1. So my expression here that I'm worried about, whether it's positive or negative, and how do I deal with the absolute values? Well, it's less than 4 and then minus 9. Clearly negative. Yeah, everybody happy? Okay, important step. Again, don't just kind of blow off and forget the absolute values. Of course, you would only be off by a minus sign, but again, it's not about the answer, it's about the concepts, and the absolute value is an important part of the calculation. So make sure it will be important in grading that you give appropriate consideration to the absolute values. Yeah.
Can you explain one more time why you changed the order? Like I understand that it's.
Well, it's not that I changed the order. It's that I recognize that this expression in here is negative. And when you have a negative expression, the absolute value of it is the negative of it.
Got it.
Is that cool?
Yeah, no, I missed the fact that it was 0 to 1 and not just positive.
Oh, okay. Yeah. Yep. Yeah. No worries. Yes.
Would like a situation ever arise where like the expression could be positive or negative?
Yeah, that's right. Sometimes it might be, and this would be unfortunate, and this would make the change of variables a less attractive option, right? But it could be that this expression here is, positive over there and negative over here. In which case, yeah, then it's like, well, is this really a desirable, does it give me a better domain if I have to chop it into pieces anyway? It becomes less attractive. Yeah. Yep. Okay. Yes.
So to do a change of variables, you need to be given an alternative.
Nope. No, it's this, in this case, yes, but there's a whole bunch of examples and scenarios and different ways that it can come up.
Okay.
Yep. And so we just haven't gotten there yet. Yep. Okay. How are we doing? Is everybody on board? Okay. Okie dokie. So, yeah, so we've got our stretching factor, and all right, here's my integral on the right-hand side. This is what I was given. This is the integral that I want to compute for whatever reason. Again, why? I don't know. It depends. We're just assuming we have a double integral to compute here. And I know how to rewrite my dA now. My dA is stretching factor times du dv. And then I just have to plug in for everything else. So let's see here. Now, by the way, how do I know, where did this come from? That x, it would seem, is u squared plus 3v. How do I know that? Where'd that come from? Well, it actually came straight out of the g function. That was given. You can see it right here. X is u squared plus 3v. Right? Our change of variables function tells us what x and y are in terms of u and v. And so likewise, I can see right here, y is v squared plus 3u. So that y, v squared plus 3u. Everybody good? Now, what happened? Is this good? Did we win, or did we just waste a bunch of time turning one integral I don't like into another integral I don't like? There's a temptation to say, well, that integrand didn't look that bad. Now look at this monstrosity of an integrand that I have to deal with here. Clearly, the one on the left is better, right? Okay, no, because the integrand's not the problem. Right? The thing that makes this a hard integral here is not the integrand. And if you're going to get right down to it, this integrand's not that bad either. It's a polynomial. It's not quite as easy of a polynomial. It's still a polynomial, and polynomials are just not that bad, right? So we took a little bit of a hit with the integrand. Now let's talk about the domain. We had an integral on this domain, which again, horrible. That's 3 separate iterated integrals. And there are worse things to say about it that I maybe won't spend time on. We have now turned it into an integral on not only a simpler domain, but in fact a rectangle, and in fact even the world's easiest rectangle, the unit square. So huge win. Everybody on board? Okay, so yeah, so to your question, where did this come from, and how do we know what our change of variables function is or should be? And this is another one of those things that it's always different, and you've got to. It's the world is yours to use whatever change of variables functions you want that happen to be convenient for your purposes, right? So there's lots of different things you can do. Your change of variables function could be a translation, or it could stretch in one direction, perhaps. It could be a rotation. And how would you decide which of these you would want to use, or perhaps something else? Well, decide by what you want really to do to your domain. So the point is, if your change of variables function is a rotation, that means that your output domain is a rotation of your input domain. Another way to say that is your input domain, the new domain that you're getting, is it's a backwards rotation of your output domain, right? So you do have to you got to keep the order straight. Whatever your function does, in some sense, the opposite is going to happen to the pullback. As you do the pullback, so it'll undo what your transformation does. But nevertheless, this allows you to do valuable things to your domain that might again make your life easier. So let's see an example here. We've got a domain here with given corners at 4 given points. In fact, it's specifically, it says a square with corners at those 4 points. So here's our domain. Do we like this as a domain? Do I want to slice this dx dy or dy dx? Neither. I'm going to hit corners, right? If I do slicing if I do my slicing like this, then I have hit corners already there and there. And I leave it to your geometric imagination. If you slice the other way, you hit the other 2 corners. So this domain, just as a whole, I don't like this domain. This is a bad domain. Okay, so now let's think creatively. Notice no change of variables function has been given. Is there something I could do to this domain that would make it nicer? And oh yeah, right. If I could just rotate it clockwise, that'd be awesome. So the way we're going to rotate it clockwise is to realize that it is a counterclockwise rotation of the thing that I want to turn it into, right? It is a counterclockwise rotation of this square here, a nice sort of, appropriately, nicely oriented square. Is that good? Okay, so we've just made a choice for our change of variables function. And again, the choice is entirely strategic, to orient it around, we're channeling our laziness, right? I want to turn this into a problem that's going to be easier for me to do. So, okay, what is this rotation? Now, I'm going to fall back on y'all's background in linear algebra and some reminders. I'm going to hit the highlights here, but rotations are linear transformations. Correction, rotations around the origin are linear transformations. Linear transformations are represented by matrices, and matrices have the feature that their columns are the images of the standard basis vectors. So now I do want y'all to think that through on your own. Make sure that you can persuade yourself that a counterclockwise rotation by an angle theta is accomplished by this matrix right here. And again, the connect the dots we just talked through. So make sure that you can do that. I am going to assume going forward that you can write down rotation matrices. And if you have any questions, of course, come to my office hours, any of the instructor office hours, help room, what have you. Okay, so in practice, effectively, there's our change of variables function. Let's get some specifics down, though. We were, in fact, given the various corners. Let's take a look at that one. That being a rotation of, well, apparently this point allows us to write down some geometry, and in particular, you can draw this triangle there and persuade yourself that this angle is pi over 6. Geometry, trig, right? Make sure you're good with those details. And this angle being pi over 6 means that this matrix is that matrix. Okay, so now we really got our change of variables function. There it is. It turns u's and v's into x's and y's. And now we plug and chug. Got to find our stretching factor. Got to compute that determinant. It's not a hard observation. By the way, neat fact though, that when you have a, this is a weird one, when you have a function represented by a matrix, that matrix, the derivative transformation is the same matrix. Isn't that weird? Linear transformations, derivative matrices are the same matrix. That, anyway, it's just how it turns out. It's kind of nice. This determinant you can compute, and it's 1. Now, this is geometrically expected, right? Rotations don't change areas. How much do things get bigger when I turn my head to the side? Well, none. It's a rotation. Nothing's getting bigger, right? Nevertheless, keep in mind it's not about answers. It's about ideas. It's about arguments and reasoning, right? And here, questions like this, I want to see the use of the change of variables formula. And so I do want to see the calculation, even if it's geometrically expected. Okay. At this point, it's all over with the shouting. Dx dy is stretching factor times du dv. We just computed the stretching factor. It's 1. Well, to be precise, it's the absolute value of 1, which is, of course, 1. And then it's just a matter of plugging in for the integrand. And again, where do I get the integrand? Where is x, for example? Well, x is given in the change of variables function. And you can see it right here. X is that dot product. So x is that, right? And likewise, y, what is that y there? Well, y is given in the change of variables function. It's that dot product. So y is that. How we doing? Yes.
Why are the bounds 1, 0?
Yeah. Oh, I haven't gotten there yet. Oh, you know what? I probably made a mistake there. Yeah. Yeah, let me recognize that mistake in just a minute. So it is all over with the shouting. Yeah, you got to multiply some stuff out. It's not that bad. A little bit of arithmetic. We have a new integrand. The integrand, again, maybe ever so slightly harder, right? But a much easier domain, right? We had been doing an integral on a bad domain. We are now doing an integral on a good domain, no corners in the slicing process. It's a rectangle, and the miscopy, thank you for catching it. I'll get this fixed. 0 to 2 and 0 to 2. And I'm sorry, I miswrote it down here. So these should be 2s, not 1s. Yeah. Okay. Everybody good? Okay, can you use any function at all for a change of variables function? Not quite. It does have to be continuously differentiable. Otherwise, things just go south. Also, very importantly, it must be invertible. So there has to be a clear sort of like one-to-one back and forth. You can't have a change of variables function that you need it to be invertible. And I don't want to get off into the exact nature of what goes wrong if it's not invertible, but it's a problem. So rotations, for example, not a problem. Okay, now neat fact, and here we're going to come back to this notation and why this notation written as a fraction is kind of nice. I point out that if x and y are functions of u and v, and being as it is an invertible function, x and y as functions of u and v, I can talk about its inverse. And if I talk about its inverse, then u and v are the outputs that in order to get this stretching factor, I would have to take partials of with respect to the inputs x and y. It's just the backwards change of variables function. But now let's think about it. What happens though if I have a little piece of area here? What happens if I look at its image and then whatever that is, I look at its image coming back the other way? Well, it's the exact same thing. If I take a little rectangle, push it forward, pull it down, I mean, I get the same rectangle, right? Doing a function and then doing the inverse accomplishes nothing. And so on the other hand, pushing it forward multiplies the area by this, and pushing it the other way multiplies the area by that stretching factor. So the product of these two stretching factors, since it has to accomplish nothing, the product of those two stretching factors has to be 1. And another way to say that is that these things, this is just another example of these things that I have written like fractions. In here now, a different way, it's as if they behave like fractions as well. So the one is the reciprocal of the other, and it looks like we're taking the denominator of my denominator and making it a numerator, and we're taking the numerator of the denominator and making it a denominator. It looks like we're doing fractional algebra here, and we're not. Right? Really, if you get right down to it, what this really is a statement about determinants of inverse matrices. But it's easier to write it down as a statement about fractions. So again, it's a little sloppy, it's a little bit bogus, right? But it's awful convenient. Okay. All right, let me show you an example where this is a big win. This is a classic example. It is, I'm going to confess, a little bit manufactured, but actually not as much as you might think. It turns out that looking at these curves, let's see if I can get this right. Come on, there we go. Looking at those curves and these curves, and looking at the region in between that's kind of cut off by, how these four curves sort of intersect. This shape, or to be fair, a shape that is morally the same as this, a little bit different, couple of details, but morally the same as this, is extremely important in thermodynamics, believe it or not. There's this thing called the Carnot cycle, Carnot engine, it's a theoretical engine, and very powerful conclusions you can get to about the efficiency, maximum efficiency possible with an engine, a heat engine. are come about by understanding this theoretical object called the Carnot engine. And the efficiency of the Carnot engine is computed by an integral on a domain that, again, morally identical to this. So it's kind of weird. Anyway, it's so this is not out of left field manufactured nonsense that you'll never encounter in the real world. This is a very important kind of circumstance. Okay. Yeah. All right. So suppose I need to compute an integral on this domain. In other words, let's suppose I'm doing stuff with a Carnot cycle. Well, corners everywhere, right? So corner, whichever way I slice, I'm going to hit two of them. Clearly, this is a bummer of a domain. We don't want to go straight at this. What can I view this as being an image of is a hard question. But what is a convenient image of it is easy, as it turns out. If you take the right sort of clever point of view, this is a clever point of view that I did not think of on my own, and you should not think to yourself, would I have thought of this on my own? This is a clever idea that somebody showed me, and I'm going to show you, and that's how you're going to know to do this, is because it's been shown to you. So the idea is, take these things here that are being set equal to constants. So notice the green and the blue both being set equal to constants. Let those be U and V. Just follow me on this. Just take my word for it for the moment. If I choose to define my function by, let's let U and V be the things set equal to constant on the boundary of my domain over here, then let's think about what happened, or what are the various curves over here then. What happens to this curve? What does that curve look like over here in the UV plane? Well, that orange curve there is where XY equals to 1, but XY is U. So over here, it's the curve where U is equal to 1. It's a straight vertical line. Isn't that clever? Right, and likewise for all the others. Right, so that curve turns into that line, and that curve turns into that line, and that curve turns into that line. So weirdly, as it turns out, and again, this is a clever move. I wish I thought of it. Defining a backwards change of variables function this way takes a we've already long ago agreed, a bad shaped domain, and turns it into a good shaped domain. Now it's going the wrong way. It's going backwards, right? But we've connected an ugly domain to an awesome domain, and now we just got to sort of think through the details. In some sense, the punchline is this right here. If you've got your change of variables function going backwards, okay. Compute the stretching factor backwards. Fine, it's backwards. Sure, go ahead and compute that stretching factor. And just take the reciprocal, and that'll give you the stretching factor going the other way. Very nice. So yeah, so here we go. Computing the partials of U and V with respect to X and Y is easy, because these are easy partials, right? The X partials are those. The Y partials are those. I mean, that's just easy algebra there. That computes the stretching factor, again, going the wrong way. Fine, I want the other one. I want to think about how are X and Y functions of U and V, and how does that stretching factor work? Well, it's just the reciprocal. It's the reciprocal of the easy one to compute that I already computed. Everybody good? Okay, so this, by the way, is another reason why I really like this notation, because this notation, it keeps track for you of which way does it need to go. Just compute the partials as indicated here, and then when it comes time to plug into your integral, I was given this integral here, I was given an integral dx dy. I want to rewrite dx dy as, stuff times du dv. What does this thing need to be? Wait a second. Oh gosh, is my function going the wrong way? Oh gosh, it's confusing. I've got u and v as functions of x and y. That's backwards. So wait a second. Do I multiply? Do I divide? Or it's easy to get confused, right? But no problem. The notation keeps track for you. What do you multiply by du dv to get dx dy? Multiply by the thing that makes the bogus cancellation work out, right? It just does the bookkeeping for you, right? So the notation alone tells me that that's the one that I want. Everybody see how that is nice? Right. Okay. And of course, I just computed this on the previous page, and we're in business almost, asterisk, and then there's a little bit of ugliness that we need to talk about. The bit of ugliness is that the way the algebra works out when you're doing them backwards, what you're going to find is that your integrand is in terms of x and y. And I need to take an expression then that's in terms of x's and y's, and I need to, can I just plug in to pull it back in terms of u's and v's? Problem, I don't have a formula for x and y, right? Expressions don't push forward. My function's going that way, and I would have to solve for x and y. Not that I couldn't do it, but I would have to solve for x and y, it would seem, to be able to do the plug-in pullback. So there is a way around this, and that is that sometimes the integrand that you're interested in can be fairly clearly related to the u and the v that you've chosen. And it doesn't always work, but here, notice that my integrand is a product of powers of x and y. Notice that my u and my v are products of powers of x and y. So what can I do to products of powers to produce a different products of power? I feel like maybe taking a product of powers of my product of powers might get me the product of powers that I want, right? So now this is a guess. This is pure speculation, right? My assertion here that I can raise u to some power and multiply by v to some power to get the integrand that I've ended up with is a hope, right? But you can see how that's a reasonable hope. What your guess is going to be different every time, different for every question. In this case, it works out well. I end up just needing for these exponents to be the same and these exponents to be the same. And so I get a little system of equations to solve, and it's easy to solve, and boom, there's my answer. I can, the thing that I'm interested in, I've written it in terms of u and v like that. Everybody good? Again, different every time. Oh, I'm out of time. Okay, so we'll draw the line right there. Hope you all have a good day, and see you on Wednesday. Sure thing. See ya.